Hi everyone, Marc and I are former students from the University of Liege, and we are going to present you the feasibility study of low carbon ammonia and steel production in Europe. As you know, the European Union wants to be carbon neutral in 2050. In order to do so, the industrial sector needs to be decarbonised. In this scope, we studied two different processes that are ammonia and steel production in 2030. The goal is to see what are the requirements in order to be technologically and economically viable. The decarbonisation of the process is obtained through water electrolysis to produce pure hydrogen instead of classical ways that are CO2 emitting. It is assumed that the electricity comes from renewable energy. The two processes are modeled with Aspen Plus, and the costs are calculated with the turtle. After this introduction, Marc will present you the electrolyzers used in our processes and the models of the ammonia and steel making plants. I will continue by presenting the cost analysis, and we will conclude by summarizing the assumptions made during our work.
As Jean-Luc said, the decarbonisation of the processes is obtained through water electrolysis to produce pure hydrogen. The choice of electrolyzer is of a proton exchange membrane, a PEM electrolyzer. This choice is based on several criteria, and the PEM electrolyzer has characteristics that's used for this application. Indeed, the PEM electrolyzer is flexible for a fluctuating electricity supply. It is important in this case because electricity is assumed to be produced from renewable energies, and so the production of electricity might vary during the day. Then the proton exchange membrane electrolyzer is able to operate under high pressure. It is important for the ammonia process, in which the reaction occurs under high pressure too. And then the efficiency of the PEM electrolyzer is assumed to be at 85% in 2030. Currently, this type of electrolyzer is not a mature technology, but in 10 years it can be assumed that it will be mature and the efficiency taken is at 85%. Now let's focus on the modelings of the two processes. First, the ammonia production. Common ammonia production plants emit around 2 tons of CO2 per ton of ammonia produced, and here is a flow sheet of a common ammonia plant, a simplified flow sheet. So hydrogen and nitrogen react to produce ammonia, which enters then in the separation section to reach the desired purity of the product, and the unreacted hydrogen and nitrogen are recycled. The hydrogen is produced from natural gas reforming, which is the CO2 emitting step, as it emits CO2 and CO, and the hydrogen comes from the air. Then the solution to decarbonize this plant is to use water electrolysis instead of natural gas reforming to produce hydrogen. So water electrolysis produce oxygen and hydrogen, pure oxygen and pure hydrogen. The oxygen is sold to increase the economic viability of the plant, and the hydrogen is mixed with pure liquid nitrogen to react and produce ammonia, and the rest of the plant is not really modified compared to a common plant. And so the decarbonized plant will emit no CO2 as the natural gas reforming is removed from this plant, and thus we obtain then a decarbonized plant. So here is the flow sheet of our model in Aspen Plus. You can see the different sections that I have mentioned, but we will not focus on it in more details as it is not the goal of this presentation. Now let's focus on the steel making process. So common steel making processes emit around 2 tons of CO2 per ton of steel produced, but it is not this type of process that is studied here. It is the DRI process, the direct reduction iron, that is the object of our presentation. So DRI processes emit around 0.5 tons of CO2 per ton of steel, and it is the best available technology in the steel making industry, but it only represents 5% of the world's steel production. So the process consists in first reducing the iron ore. So this occurs in a shaft reactor where iron ore is in contact with countercurrent reducing mixture. This reducing gas is composed of CO and H2. And in the shaft reactor there are three steps. First the iron ore is heated, then the reduction occurs, and then the mixture is cooled because the reaction is exothermic. Then the DRI enters in the electric arc furnace, an EAF reactor, in which it is mixed with other components to produce steel and other byproducts. And so in this process, the reducing gas is made by natural gas reforming, which produces CO and H2, and it is the step that is replaced by water electrolysis in the decarbonized plant. So water electrolysis produces oxygen and hydrogen, and this hydrogen is mixed with a small amount of CO to obtain the reducing gas in the decarbonized plant. This small amount of CO is required to avoid too high reactivity of the DRI obtained after the reduction. So the reducing gas is in countercurrent with the iron ore in the same shaft reactor, except that here the shaft reactor, the three steps of the shaft reactor are first heating, then the reduction, and as the reaction is here endothermic because of the great presence of hydrogen, the third step is a deeper reduction as no cooling is required. The rest of the process is similar. It enters into the EAF reactor and the steel is produced. Just to mention, the oxygen that enters into the EAF reactor could be taken from the electrolysis as it produces pure oxygen in addition to hydrogen. And this decarbonized process only emits 0.15 tons of CO2 per ton of steel produced. So here is the modeling of this process on Aspen Plus. Again, we will not focus on this specific modeling as it is not the point of this presentation, but you can see the different parts that I have mentioned.
Based on the models, the costs of the processes can be calculated for the case of a grassroots plant operating 8,200 hours per year. The main variables that influence this cost are the capex of each equipment and the opex, and more particularly the electricity price, due to the large electricity consumption for the electrolyzers. The CO2 taxes that will impact the profitability of common plants that emit large amounts of CO2, and the products and raw material costs. And now, let's focus on electricity price. As we can see on this graph, a common ammonia plant consumes 100 gigawatt-hour per year. Switching to a decarbonized ammonia plant, the consumption increases to 5,000 gigawatt-hour per year due to the electrolyzers. This level of consumption corresponds to an aluminium plant. The price corresponding to the electricity consumption is generally around 40 euros per megawatt hour. A peak shaving approach can be considered to decrease even more the electricity price. Peak shaving consists in decreasing the electricity consumption when the demand on the market increases, allowing to negotiate a lower price with the supplier. The model considers an electricity supplier of 18 hours per day, during which hydrogen is produced in excess and stored to keep a steady production during the whole day. This approach leads to a price of 30 euros per megawatt hour, which will be considered in the rest of this work. Now that the price of the electricity has been fixed, a sensitivity study can be conducted for each process on the most sensitive variable. For the ammonia process, the cost of the CO2 emissions paid by common CO2 emitting plants has the biggest impact on the viability of the plant. In order to be economically viable, with a price of electricity of 30 euros per megawatt hour, the CO2 price must be of at least 225 euros per ton of CO2. Currently, the cost of a ton of CO2 emitted is around 25 euros per ton in Europe, but its value should increase in the coming years from 50 to 100 euros per ton. Moreover, additional taxes on CO2 could be raised as it is planned in the Netherlands. Its value could go up to 150 euros per ton in 2030. If the price of electricity was less than 30 euros per megawatt hour, the required taxes could be lower and the plant would still be viable. We can see in the discounted cash flow diagram that with a CO2 tax of 250 euros per ton, a discounted rate of 10% and an ammonia price of 350 euros per ton, the payback time is around 15 years. In the case of the steelmaking plant, the sensitivity study is conducted on the price of steel itself, and it has the biggest impact on the viability of the plant. With an electricity price of 30 euros per megawatt hour, the cost of the steel must be of at least 635 euros per ton. As for the ammonia, if the price of electricity was less than 30 euros per megawatt hour, the required price of the steel could be lower and the plant would still be viable. We can see in this discounted cash flow diagram that with no tax on CO2, a discount rate of 10% and a steel price of 840 euros per ton, that is actually the price of steel in 2018, the payback time is of only 8 years.
To conclude, let's summarize the assumptions that have been made to reach feasible processes. So first, the PEM electrolyzer needs to be a mature technology in 2030 with an efficiency of 85%. Then the electricity price needs to be negotiated. As we said, it is the most impacting factor in the cost of the two processes. And so reducing this electricity price would allow to increase the profitability of the plants. We mentioned the peak shaving approach. That is one of the solutions to decrease this electricity price. Then we also made the assumptions that the electricity was entirely supplied by renewable energies. So it is utopian to say that in 2030 it will be the case, but this assumption has been made to focus only on the goal of our project, that was to focus on the feasibility of the two processes. Of course, decarbonizing the industry and switching it to only electric plants would be irrelevant if the electricity supply was not green. If now we focus on the two processes, first the ammonia plant, we have seen that the most impacting factor is the price of the CO2 taxes for the other common plants that emit CO2. A large increase of the CO2 taxes would increase the profitability of the decarbonized plant for the ammonia production. And for the steel making process, it is the price of steel that is the most impacting factor, as this price varies a lot each year. Assuming a higher price of steel is a possibility that would allow to obtain a profitable plant for the decarbonized steel making process. Here are the references of our presentation, and we thank you all for your attention, and if you have any question, please feel free to ask.
Yeah, thank you very much, you two, for this new way of making a conference digital. You really made a step forward, not only digital meeting, but also a digital presentation. So thank you very much for this. Are there any questions? As you may know, at the moment, I'm the only chair of this session. So are there any questions from the audience or from the speakers? I checked it on Google, but so far there are no questions. But maybe I can ask, I think, Marius, you are quite familiar with these technologies with ammonia production and steel production. Do you have a question for your co-speakers?
Not directly. I think I should have the presentation in detail to have a look at the cost.
Okay, that's
yeah,
completely
quite
fine.
Interesting presentation. I think it will help us a lot in our future work, maybe.
Yeah.
But it would be interesting, maybe, I don't know, did you write a paper? So the assumptions behind your cost curves or your cost estimations would be very interesting.
We wrote a paper, so we can send it to you on your email.
But you also wrote a eceee paper. It was not me who reviewed the paper, it was my colleague. So, but you wrote, it's a peer-reviewed paper. It's not only a conference, it's not an oral presentation only, but you also wrote a paper, I think, right? Yeah. So we will get the paper later on. But I have a question. So you have 3 elements in your presentation. You have the PEM electrolysis, you have the ammonia production and the steel production. How come that you look at these 3 elements at once? Why didn't you pick just one, or how came this setup of your research?
In fact, we participated to a student contest last year who focused on the decarbonization of industries, and 2 of the industries that were studied were the ammonia and steelmaking processes. And the PEM electrolyzers, we had to use electrolysis to achieve this decarbonization, and we had chosen this type of electrolyzer because of its characteristic, as I mentioned in the presentation. We studied different types of electrolyzers, and we chose this one because it best suited the application. But it was part of another contest, in fact.
Okay. In the earlier session, I'm not sure if you have attended the previous session at 12. There we had a presentation from Anna Labrand from the Wuppertal Institute, and there she found that using electrolyzers at the moment with the current electricity mix in Germany is not yet CO2 efficient comparing to other hydrogen production technologies. But I think you considered France, and I think you have another CO2 emission grid factor in France. So for you, using grid electricity already leads to low carbon hydrogen already? Or how is the CO2 emission factor of the hydrogen you generate with the electrolyzers?
In fact, we assume that the electricity was produced from renewable energies. I know that it's a big assumption to say that, but our work was more to focus on the feasibility of the processes and how is it technologically and economically viable. And we just assumed that it was a renewable electricity, even if we know that it may be a little bit unrealistic in 2030. But again, the 2030 year was the statement of the contest, in fact. So we were a little bit linked to that statement.
Maybe one comment on that, Marlene, if I'm allowed to.
Of course.
I calculated the hydrogen emission factor for electrolyzers compared to steam reforming for the electricity mix in Germany a few weeks ago, and in my calculations it was about factor 5 higher than steam reforming by using the current electricity mix for water electrolyzers. So
5 times.
Yeah. Factor 5.
Yeah. So that was what Anna Leibrand said as well, that it's more CO2 intensive. Okay, and another question: did you check your results with someone from the chemical industry or from the steel industry?
we had some contacts with people from ammonia and steel industries, and they helped us in our project. And so we discussed with them to see if the results were coherent, I say, and I guess they were. So they said that was the case.
So you could imagine that by 2030, given a certain CO2 price and a certain price for steel, it's feasible that steel and ammonia is produced using hydrogen?
It seems difficult at the moment, but someone will have to pay away another. So we have to increase the CO2 taxes or reduce the electricity price for these industries. That seems to be the only way, but someone will have to pay.
And you have taken the electricity price of 30 euros per megawatt hour, right? Yes. What do you think about that price?
It seems possible, but with only renewable energy, maybe in 2030 it's a bit early.
And is it a French industry price for electricity, or where did you take those 30 euros from?
So we based our paper on another paper that considered the price of electricity in Europe. And for the moment, it was 70 euros per megawatt hour. So it's after the peak shaving and a big consumption that the price can get lower.
Yeah.
Can you maybe say something about why the PEM electrolyzers is better than the alkaline electrolyzers for these applications, or which parameter are the most important for these differences?
In fact, it was the flexibility of the PEM electrolyzer that is the main important characteristic, because for the alkaline electrolyzer, as we suppose that the electricity came from renewable sources, and as we wanted to do a peak shaving approach, we had to be able to stop the production with the electrolyzers, or to cope with fluctuating electricity supply. And so, as the alkaline electrolyzer is less flexible than the PEM electrolyzer, we had to choose the PEM electrolyzer.
Okay, thank you.
Okay, thank you very much. I make a final check if there are any questions on Wouver. Maybe Abena, you would have mentioned me to, or you have told me if there were. I think there are not. So thank you very much for your interesting presentation and for the innovative way you have chosen to do that. Thank you very much. And we're looking forward to read your paper. I think Marius and me, at least, we will read it, and maybe some more from the audience as well. So thank you very much for a nice presentation. And with that, I hand over to Marius. So please, Marius.
Yes, thank you. I will wait for my presentation. Maybe we have to wait a second until Abena has my presentation online, because there had been a problem with my format before. Marlene, you are muted.
Sorry, Abena just asked you to share your screen. Oh, now there is.
Yes, great.
Yeah.
Okay, then thank you very much for the introduction, and welcome to my presentation that is about the potential and the possible transformation path of the German chemical industry, or maybe more precisely some of the basic chemicals, also ammonia. And here at first, let's have a quick look at the agenda. Can you see the next slide? Oh, yes. Yes, at first, a quick look at the agenda. At the beginning, I will shortly give some information of the political background, which is also the motivation behind it. Then I'm going to present the methodology and how the results have been generated before showing them, and giving a short summary at the end. I think we all know the motivation behind it very well and have also heard it several times before in this conference. And the first part is, of course, the Paris Climate Convention that was adopted in 2015 together with the 2 degrees target by 2050. And in 2018, this target was even tightened to 1.5 degrees. The second part is the German climate protection law, which was passed in November 2019. And here the aim of climate neutrality until 2015 is stated. Also, the chemical industry is one of the energy-intensive and emission-intensive industries. And in Germany, the chemical industry accounts for about a quarter of the total industry emissions. No, not the emissions, the energy demand, of course. And for decarbonization, a switch to climate neutral and regenerative technologies and energy sources is essential to meet the climate targets. And yeah, that could be happened by direct or by indirect use of green electricity. Then also the generation of storable energy sources to balance some fluctuations on the supply dependencies of renewable energies. For example, by wind or photovoltaics is very important, and as well the additional use of these synthetical energy carriers as raw materials or even as feedstock will play an important role. And a medium that seems to be very well suited for these technologies or these purposes is, of course, hydrogen. And here we can come to the research question: what role can hydrogen play as feedstock in the transformation of the basic chemical industry? And this also leads me to the methodology. First, an extensive overview of a conventional and also alternative hydrogen-based production routes had been conducted, and here the focus was on ammonia, methanol, and ethylene. Then the second step was matching these informations with our industrial site database. And here a determination of the status quo. Oh, sorry. Let me go back. Yes. And here the status quo of the German plant stock had been carried out. And then on the basis of the age structure of these plants, I calculated a possible transformation pathway of the chemical industry. Then the third part had been benchmarking these results to a literature scenario. And this scenario had been carried out or done by some colleagues of me for DG Climate in 2018. And out of this scenario, I took the results for Germany. And the scenario 4B mix 95, which is a 95% reduction scenario with a quite balanced mix of energy carriers. So this scenario is also consistent with a political framework, or was in line with the political framework before the EU Green Deal. And there we calculated the energy demand with our simulation tool Forecast. I don't know if anyone was online yesterday, because Tobias there told about Forecast and gave more insights. So in Forecast, the plant stock and the age structure had not been considered in detail, but the processes were implemented, and based on the annual productions, the annual production volumes, and some statistical curves for the modernization, these plants and these processes are implemented. Then we will come to the first results. Yes, here on the right side, you can see the locations of the plants with the production capacities in Germany, and the left side shows the replacement or replacement cycles for the plant renewal in percent in the several decades. But I think I will directly go to the next, because there we can see that in more detail. So here we have the cumulative production volumes in megaton per year of these three basic chemicals, so ammonia, methanol, and ethylene. And the turquoise is the diffusion of the hydrogen-based technologies into the market based on the H structure. And yeah, as you can see, there are some highlighted lines in 2030, 40, and 50. And here we can see that until 2013, about 2 megatons per year are replaceable until 2030, and that accounts for about 20% of the ammonia plants, 50% of the methanol plants, and 33% of the ethylene plants. And until 2040, we have around 5.5 megatons per year that are replaceable, which includes 80% of the ammonia plants, 75% of the methanol plants, and 55% of the ethylene plants. And then the same until 2050, where we then come up with 7.2 megatons per year that are replaceable due to the H structure. And this represents 100% of the ammonia plants, 100% of the methanol plants, and 78% of the ethylene plants, which also means that 22% of the ethylene plants are not at the end of their theoretical lifetime until 2050 and could even be renewed after 2050. So when we then have a deeper look into the capital investments in the several decades, yes, here we go. You can see that from on the right side, from 2021 to 2030 and from 2031 to 2040, we have about 8 billion euro investments that have to be done due to the H structure renewals. And from 2031 to 2050, there are around 6 billion. After 2050, we have about 3.7 billion euros left. And if we go with the target of climate neutrality until 2050, we have to put that into the decade before. And then here we go, nearly to 10 billion euro. And this all results into cumulative capital investments of about 26 billion euro until 2050 to replace all the plants we have in Germany for these three basic chemicals. Maybe one key finding of this calculation was that the MTO route for ethylene is very intensive. So therefore, about 55% of the total investments account for ethylene via the MTO route. On the next slide, we go to the operational cost or the operating cost. And what we can here see is that they have also been calculated for 2030, 2040, and 2050. And there I combined the invest with the OPEX costs and compared them. And the most important point is here that the investments have quite a low impact on the annuities, and that the biggest share of the OPEX is the OPEX due to the electricity cost. And the electricity cost is that high because we need so much, hopefully green electricity, to produce the hydrogen by water electrolyzers. And here on this slide, I just put some more results for the end year 2050 due to the time. And here in 2050, we can see that we could need around 3.5 megatons of hydrogen per year for these three basic chemicals. And under these assumptions, or one assumption behind this is stationary production based on the year 2018. And therefore, we would need about 180 terawatt hours per year of green electricity, and about 60 megatons per year of greenhouse gas emissions could be saved annually. And here, this is all for 100% replacement to green production routes until 2050. Then to come slowly to an end, we will have the summary and then the benchmarking with the scenario and some conclusions. So 100% renewable electricity is essential for CO2 savings with alternative technologies and also nearly 100% of the plants are at the end of their theoretical lifetime until 2050. But yeah, here of course I have to say that often these plants get partly modernized, so that it's quite difficult to be precise with this theoretical lifetime. So even talk about something like theoretical lifetimes, because partly modernization, these plants can even stay 100 or 120 years or even longer. Also, Florian Ausfelder from Lechtenböhmer yesterday told or talked about that. Then the benchmarking with the scenario 4B mix 95. The difference to this pathway was that there the diffusion for hydrogen technologies starts around 2030, whereas in the calculation here the plants are even at the end of their lifetime some years before 2030. So I assumed an earlier market entry for these technologies, and yeah, this also results in an underestimation of the 4B mix 95 scenario for 2040. And what we can see here is that for 2050, the energy demand is quite equal from my calculations to the scenario calculations of 2018. Yes, and I think the conclusions there, I already had most of them. So the production or the operating costs and thereof especially the energy cost for the green electricity are the most interesting parameters for subsequent considerations, I think, and also prognosis and life cycle estimations are quite difficult due to the partly renewals of the plants during their lifetime. And what also could be very interesting at the end, or for us very interesting at the end, had been that the scenario for BMix 95 fits for 2050 quite good to the calculations I did bottom up here. And yes, then I'm at the end of my presentation. Thank you very much for listening, and please come up with some questions. And here's some contact data if you want to contact me afterwards.
Yeah, thank you very much, Marius, for this great presentation. Are there any questions so far?
I can ask a question if that's okay. It's Emrah.
Yeah, please, Emrah, go ahead.
Perfect. Thank you very much, Marius. Very interesting presentation. We've done similar studies, and we've been asked by governments and private clients on similar topics. So what's the kind of pathways to net zero in industry, including chemicals? And obviously, we do look at similar parameters like end of lifetime replacements and remaining lifetime, etc., which is really helpful. But I guess the thing I'm still struggling to imagine is what would happen in reality, because these will happen with some sort of incentive policy or, let's say, demand from consumers. So the market needs to transform at some point in the near future. Let's say in the 2020s, only individual projects go ahead funded by, I don't know, innovation fund and member states and so on. So there's not significant impact on the whole market. But at some point, I'm imagining the 2030s and 40s, there has to be a change in the whole market, which will drive significant investment in decarbonization industry. I guess my difficulty is, what do you think will happen to the conventional plants when there is significant demand for low carbon chemicals and there is significant incentives available for the sites, let's say, that still have 20, 30 years remaining lifetime? Do you think they can still wait until 2050 or beyond, as you said, or will they just simply retire early, or maybe consider retrofit options, or I don't know, maybe they'll just unfortunately go bankrupt and shut down sites? Just trying to understand, what do you think could happen in reality if there's significant market driver for decarbonization, deep decarbonization of industry, let's say in the 2030s and 40s, in that kind of significant to the case that you showed, most sites may at least consider replacement?
Yes, thank you for that comment. I think you're absolutely right. Maybe the economic question, I don't think that it will be economically feasible until maybe 2040. But the big or a huge problem behind that is that the political framework doesn't give the new technologies a chance to enter the market, because we have so much taxes, and renewable energy sources are, or especially the green electricity, is much too expensive, and the CO2 prices are much too low that there would be a market entry due to economical parameters. So I think it's not on the industries or the manufacturers to implement these technologies. I have the experience that they are willing to do this, but what they always say is that they don't see any business case behind implementing these technologies. And there it is. I think it has to be a target of the politics or the politicians to making some laws, or even showing them some ways, some possibilities to having a business case in these in implementing these technologies. Otherwise, we won't have these technologies the next 10, 20, maybe 30 years, I think. And then maybe there is a danger to run into lock-in effects, because if any plants, if it's the chemical industry or the steel industry or anything else, doesn't matter, but if any plant is at the end of the lifetime and it gets replaced or modernized, and then we plan again conventional technologies, then we have lock-in effects, because then we have depreciations of about maybe 20, 30 years, and then we are definitely after 2050. So I think it's on the politicians to act.
Perfect, thank you.
Thank you very much, and also thank you very much for this great question, Emrah. Okay, so there's another question. I will read it out to you, Marius. It's from Richard. From what I have learned at this conference, the life cycle for chemical plant can be easily extended. Do you agree that this is correct? And does this have an impact on your modeling?
Yeah, I fully agree with that. The life cycle, or the theoretical life cycles, as I said, can be above 100 years if the plants are partly modernized over their lifetime. And yes, that will have an impact on my modeling. I assumed an average lifetime of about 60 years, which is quite long, I think. In literature, you often read from 40 to 50 years, and due to the partly modernization, I have the estimation of 60 years. And yes, that is what I said at the end of my presentation. So life cycles of about 100 or even 120 years are possible. And so here we are again at the question of who has to act that we can implement green electricity and green alternative technologies. And here it is the politics. They have to implement the conditions that we will get a business case out of that, and that yeah, it's definitely important for the modeling. But you have to assume a life cycle or a time for life cycles that you can do any kind of calculations. And yeah.
Thank you, Marius. There is another question from Johan Rosen. So linking back to the discussion in the previous session, what do you think about the risk of production leakage to regions with lower renewable electricity production costs, for instance, to the MENA region?
Yes, very good question. That is also why in my calculations I divided by at the cost, at the operating and investment cost, I divided into synthesis unit and electrolyzer unit. So these calculations are for complete new plants. So if you just want to go to alternative production, maybe you can hold the synthesis unit and just build new electrolyzer units. But if we think that maybe the production locations could change, maybe to MENA or in Germany, even to the north of Germany from the south, there are higher investment costs because you have to build a synthesis unit of ammonia or methanol also. But yeah, of course, there is a risk of leakage, and the MENA region will be able to produce green electricity and green hydrogen much cheaper than we are able here in Germany, I think.
Yes, I think that's one of those points. Thank you for your answer, Marius. There is no more question in the chat as far as I can see. If there are any other questions, please raise up. I have another question to your presentation, if I may add, Marius. Are you still able?
Yes, of course.
Yeah, okay. So in your presentation, you have shown that starting from 2020 onwards, there will be a shift to alternative technologies, to low carbon production sites in the German chemical industry. I think this is not really realistic. I think the political framework is not yet set that companies can start this year. I think they need like 10 years in advance to plan and commission the plans and etc. So when you shift your calculations 10 years into the future, then the picture would look quite different in 2050, right? So are we already behind to reach the climate goals in the chemical industry in Germany?
Maybe we are. I think that we can go back to the question, what are the life cycles of these plants? So with the 60 years, now we definitely have plants that are at the end of the theoretical lifetime in the next 10 years, but there is no problem operating them 10 years longer, I think. And maybe we have to be more, or the change has to go faster then, if we just start 10 years later. And you saw the comparison with the benchmarking with the literature scenario. So if we go 10 years later, maybe we have the same route as my colleagues calculated with forecast. And yeah, maybe also here again, the risk of lock-in effects by implementing new conventional plants are given, but especially in the chemical industry, I don't think that we can also reach climate targets if we go 10 years later, but we have to show, or have to try being as fast as possible.
Okay. And then the last question I had in mind was, there was a comment from Diana Powers, just that Portugal and Morocco plan to dedicate for PV photovoltaic construction for hydrogen. Yeah, I think Australia has done that as well. And now I forgot the question I had, but I can ask it to you someday later, I think. So yes. Also a warm welcome to put other questions into the Woover. And please, all the speakers, go there and see if there are any questions for you that you may answer. Okay, so thank you very much, Marius, for your presentation. Good luck with your work. And now I remember my question that I say thank you. So the question is, did you check your results with the chemical industry in Germany? Did you discuss your results with them, and what do they say?
Yes, partly. We had one workshop with people from, I think, Covestro and BASF, and yeah, their argument often have been the high investment costs of electrolyzers, but as you can see in this study, the investment costs are not a parameter that is really important for implementing or not implementing these technologies. So it definitely are the costs for green electricity. And yeah, we definitely have to go more into the industry and discuss the results with them. But yeah, I think more activity will be in the future to take or make new contacts with them and discuss the results with them. Yes, yeah. We definitely have to do that.
Yeah. Okay, so thank you very much, Marius.
Thanks.
And yeah, just a few more minutes and then the conference is nearly over. So now we come to our last presentation from Emrah. I'm very delighted that you will present, and I'm very much looking forward to your presentation, Emrah. Please.
Thank you very much, Marlene. And I believe my slides will be up in a second. Yeah, something is happening. That's promising. And I'm controlling it. That's perfect. Thank you very much, and good afternoon, everyone. And this is the last presentation of the last panel of the long conference. So hopefully, thanks for surviving this far and attending this interesting panel session. So what I would like to do in this session is I would like to talk about some of the kind of wider technologies needed for net zero industries, as well as the wide range of messages regarding the decarbonization of industry, and especially deep decarbonization of industry. Building on our experience mainly in the UK. As you know, UK implemented the net zero targets legally, which is great, and we've been working heavily on a number of different sectors within the organization, including industry. So that's why, and we have a lot of kind of big projects and potential projects in the UK, mainly on decarbonization of industry and industrial clusters. So I'll try to share some of the key learnings and messages from the kind of early development of these interesting projects in the UK. But before I do that, I would like to introduce myself and my company. So I'm Emrah, Durusut, an associate director at Element Energy. So we are a low carbon energy consultancy based in the UK and with offices in France and Australia. As you can see on the slide, we cover a wide range of different sectors, from industry to transport, buildings, networks, energy systems, etc. We do have a dedicated green hydrogen team as well, who has been leading a significant chunk of the kind of green hydrogen initiatives and projects across Europe. But my team, I'm leading our CCS and industrial decarbonization team, and we've been working on blue hydrogen concepts heavily over the last couple of years with some major project developers and governments. I do know blue hydrogen is not very popular everywhere in Europe, but in certain countries like the UK and Netherlands, maybe Norway, it may play an important role. Okay, moving forward to the next slide, hopefully, I think there's a delay on my presentation, apologies. Okay, so this is a kind of snapshot of what may be needed to get to net zero industry in the UK and beyond. So when we say industry, it's very easy to just say industry, but as you know, there are so many different sectors and processes and different types of energy requirements and heating requirements across different sectors. On this slide, I'm showing the kind of major ones, which are typically included as, let's say, the energy intensive industries, iron and steel, cement, chemicals, etc., but also, refining, glass, paper, food and drinks, and so on. But there are other sectors as well, which are not really commercial buildings. They still have processes and they also need to decarbonize, such as, car manufacturing, for example, which are not shown on this slide, but you can try to apply same messages to those industries as well. So in terms of the different types of technologies that may be needed, historically, we focused more on electrification as the kind of key way to decarbonize industry. But for a number of different areas, such as process emissions from iron and steel, cement and others, electrification doesn't really help, unfortunately. For very high heat applications, still, electrification technologies are not there yet, and it may not play a significant role for certain heating applications too. So electrification will be important, but we need other technologies too, if you're serious about net zero or deep decarbonization of industries. And namely, we will need biomass, if it makes sense. We will need hydrogen. We've done some studies on this, and previous speakers also talked about potential use of hydrogen in the industry. Carbon capture and storage will be important, especially for process emissions, as I said, because without CCS, it is really difficult to capture process emissions, even if you replace all the other field requirements. That still stays there, and quite a significant chunk of industrial emissions come from process emissions and negative emissions. So even if you do your best, there will always be some struggling, let's say, industrial sites, maybe in the middle of the continent, far away from, for example, there are some dispersed industrial sites which may be difficult to decarbonize. Maybe they won't have access to hydrogen or CCS, and maybe some processes will remain unabated. So the only option for them may be to go out and maybe buy certificates from negative emissions projects. So we will need a wide range of different technologies and decarbonization options to get to net zero. And as I said, hydrogen and CCS will be important for industry. And on this slide, we try to illustrate why CCS and hydrogen is really popular, are really popular, at least getting popular in certain countries, for example, the UK and the Netherlands and Norway. So I think in summary, with CCS and hydrogen, you can pretty much decarbonize anything. Along with electrification, this can tackle pretty much all sectors and all emissions. So in other words, you can maximize your electrification effort as much as possible. And for the remaining annoying emissions, you will then need to rely on a combination of CCS and hydrogen. And when I say hydrogen, it includes both blue hydrogen and green hydrogen. And for CCS, obviously, you can, more importantly, decarbonize industry, especially the process emissions, as I said. You can provide negative emissions combined with biomass. It doesn't have to be in power sector. I know there are some big power projects in BECCS, but you can do this in industry even. If you have biomass in cement and apply carbon capture, even a cement site can become negative emissions, for example. You can decarbonize power generation as well, potentially, but I guess that may only help after renewables. And also, as I said, you can produce blue hydrogen. And within a couple of our studies, we also looked at whether we can produce net zero blue hydrogen. And that's feasible if you include some biomethane along with natural gas in your APR, for example, then you produce hydrogen. So technically, you may be able to produce net zero or even net negative hydrogen with CCS. And secondly, looking at the hydrogen angle, yeah, it's very similar. You can decarbonize transport, you can decarbonize heat and elsewhere with hydrogen as well. So that's why certain countries in the UK and elsewhere are getting excited about those two technologies and fuel types to be able to decarbonize, have optionality in their countries to decarbonize sectors. And because of that, in the UK, these are 4 of the kind of big clusters, and we have others as well, and all of them have potential projects across the country. And you can see from these diagrams, maybe some of them are a bit small, but you can see that pretty much all of them include a combination of CCS and hydrogen within their industrial decarbonization concepts, of course, as well as renewable energy and electrification. But I guess, because we already have extensive offshore wind and it's already growing heavily, I guess the key gap here is CCS and hydrogen. That's why we're seeing those included in these early projects in the UK, and from Northwest to Humber and Scotland and Teesside, and quite well-known international organizations and as well as local organizations are involved in those projects. So yeah, they are progressing well, and they all include a combination of CCS and hydrogen and electrification within their project plans. So we also, as I mentioned, the use of hydrogen. I'm going to talk about the use of hydrogen in industry a bit in a later too, but before coming to that, actually, I want to say a few things about hydrogen for heat. I mean, in certain countries, as you may have heard, use of hydrogen to replace natural gas within the heat system is becoming popular. And we did a study for the UK government as well as for Equinor on this topic before. We first looked at industrial users as a potential barrier for hydrogen for heat conversion, because they were mainly interested in domestic and commercial buildings, and they were worried that if they convert as part of the gas network into hydrogen, some industrial sites will be connected there, and then the question is, what are we going to do with those industrial sites as a potential barrier? But actually, over time, we now think that especially in the UK, we think industrial use and industrial heat could be the early users of hydrogen. And it's a lot easier to convert industry to hydrogen because they are mainly located in industrial clusters, and that's where we are expecting large production of hydrogen, both for blue and green. For green, for example, you have access to offshore wind, and you can produce significant large-scale hydrogen. There are projects in the UK and Netherlands, for example, on this topic. Again, for blue hydrogen, you need to be close to these industrial clusters next to shorelines to be able to capture CO2 and store offshore. So, and these industrial sites are already there, and with just 1 or 2 industrial sites, you can enable a large-scale hydrogen production project, because then you have only 2 users who will need to switch to hydrogen, for example, instead of thousands or maybe hundreds of thousands of domestic users. So that's why there's a trend towards industry first and heat next in those type of concepts across Europe. Again, in countries where which are interested in hydrogen for heat. As I said, we also looked at the use of hydrogen in industry. This was a study for the High for Heat program in the UK, and we looked at the retrofit of industry to hydrogen. So that's a quite interesting concept because, you know, as we just heard about from the previous discussion, end of the lifetime replacement and this kind of investment lock-in is a pretty big problem for industry. And we were interested in understanding whether we can actually retrofit existing gas appliances to hydrogen to overcome this problem. And it is, apologies, it is technically feasible to convert pretty much all existing natural gas equipment into hydrogen. So obviously we didn't do all the technical calculations. We worked with Jacobs and international consultancy and a university in the UK to look at this in more detail. But the conclusion is that although we identified some potential barriers, it is possible to convert the industry, existing natural gas equipment in the industry to hydrogen. Having said that, there are some couple of key barriers there. For example, the impact of changes in ready-to-heat transfer is a big problem on glass industry. So we are working with the glass industry to overcome those issues. NOx emissions may increase with hydrogen, so there are some problems there. And I have a list on the slide in the table on the left-hand side. There are solutions and enablers for all of them, but that will require demonstration. So that's the key action for Europe, if they would like to see hydrogen use in industry, is to demonstrate the technical feasibility and safety of hydrogen use in pretty much all sectors. And the slight challenges there, when we talk to each individual industrial associations and users, pretty much all of them said they would like to see a sector-specific demonstration. So it may not be as feasible to look at a, I don't know, ceramics kiln demonstration project and convince every other kiln user in industry, for example. So they would like to see a sector-specific and sometimes equipment-specific demonstration, which will mean we will need so many demonstration projects. Luckily in the UK, some of them are already ongoing, funded by the government, but we will need a lot more to convince industrial users and investors. And this is my final slide. Apologies if I might use my time already, but this is my final slide. So I do know this session is more about technologies, but I already made some comments on the importance of policies and business models. And as I said, the reason being is that none of them will happen unless there's a serious change in the market drivers. And that doesn't only mean incentives, but we're, the Europe is talking about a number of different things such as border adjustment tax, procurement rules, etc., etc. So different things are already happening. But we will need to create incentives and enough driver for industrial organizations to make these serious transformational changes and investment in the low carbon technologies. This is a slide based on our work in 2018 for the UK government on industrial CCS business models. And we looked at a number of different business models for CCS. The reason I'm showing is that because I think these type of models should apply to pretty much all industrial decarbonization projects across Europe. Very briefly, the first one is the contract for difference based on carbon price. This is similar to the contract for difference arrangements in the power market based on electricity price, but this is based on CO2 price, for example, EU ETS. And since 2018, actually, this has become really popular, and we are now seeing this even in the EU Green Deal, and also the UK government has chosen this business model for industrial CCS. So I'm going to mention a few others, but actually, this is maybe the winner. In the kind of business model race for industrial decarbonization and CCS. But there are other options as well, like cost plus and regulated asset base. These are very straightforward models. That means pretty much all costs are covered by the government, but this is not very easy. These are not very easy models if you have hundreds of, CCS projects or decarbonization projects across Europe. These are very helpful for the early movers, let's say. Then other options include tax credits, similar to the US. In the US, the CCS and the decarbonization industry is driven by some tax credits. CCS certificates was an idea that was mentioned by us and others to drive investment in CCS. But yeah, that brings some complexity in terms of administration. So that's why there's not much appetite on that one currently. And then low carbon market creation is a really important one, in my opinion. This is basically, this shouldn't work on its own, but this can be implemented tomorrow. That's some progress already happening. The idea here is that there is no, instead of incentivizing only technologies like specific hydrogen technologies or CCS technologies, we should go out and incentivize products. So we need to create demand for low carbon steel, low carbon cement, low carbon chemicals in Europe and beyond. And the way to do that is, we can already do that tomorrow by including embedded carbon in buildings, for example, so that, building construction companies at least consider the cement that they use in their buildings, or car manufacturers at least consider the steel they use in their cars. So thinking about carbon and embedded carbon will not enable billion-pound CCS projects straight away, but that will create some good market signals. So that low carbon market combined with contract for difference will be my preference, I guess, within that list. But again, there's some optionality for the European governments. I think that's all I would like to say today. Apologies, I talked about so many different things, but hopefully that was a useful kind of final presentation to wrap the whole sessions together, maybe on the decarbonization of the industry. And my email address is there, and happy to take questions now. Thank you very much.
Yeah, thank you very much, Emrah, for this great presentation. You touched upon quite a lot of topics indeed.
Yes.
But it's really good as a final presentation, even more. So are there any questions? I checked it. So far there are, yes, there is. So just a second. So difficult, huge question, but according to you, what will be the main effects of Brexit on the timely decarbonization of the UK industry? You can think about the answer, and do you want to know who asked this question as well? Doesn't matter to you?
Yeah, Brexit is a difficult topic.
It's from Johan Rosen from Gothenburg, so he asked this question. So very good question, Johan.
Yeah, I think Brexit is a difficult one, to be honest. I guess, Brexit is just an example. So when we work on decarbonization of industry, obviously we sometimes work on in isolation, only considering climate change. But in reality, there are other problems, unfortunately, such as Brexit that may have an impact on the markets and industries. We had a similar issue, for example, some of the suggestions that we include in our reports, such as carbon leak, to tackle carbon leakage, could include border adjustment tax, but when United States and Trump does that, it may almost lead to a trade war with China. Those type of things are really complex, and it's not as easy as let's go out and invest in these technologies, unfortunately. And Brexit, as I said, is one of the examples in showing how complicated industry is, because it's international and trades are happening between countries, within Europe, between UK and Europe, but also internationally as well, especially for steel. So I guess the answer is very uncertain. The UK is proposing to have its own carbon pricing mechanism, and they already explained how that would work. Obviously, we'll need to wait and see how the deal will be with end of this year, hoping there's a deal. And then maybe if you ask me again in January 2021, I'll be able to provide a reasonable answer. But yeah, currently it's really difficult to answer the impact of Brexit without knowing what the deal will be. But I guess, that's just wanted to use this question to demonstrate that industry and industrial decarbonization is really complicated, and there's so many other factors that will have an impact on these decarbonization pathways.
Okay, thanks for your answer. There is another question, just a second. So, do you think there would be a potential role for industrial symbiosis in promoting hydrogen?
Industrial symbiosis to promote hydrogen. I don't know who asked this question, but it will be great to understand.
It's from Reza Vahid-Sadeh. I'm not sure.
It would be good
so
to
once
understand.
Again, do you think there is a potential role for industrial symbiosis in promoting hydrogen? I guess, if I may translate it to you, as I understand this question, is that if you have two companies and they both need hydrogen, would that be a push for hydrogen?
Yeah. So I think, maybe just the terminology, you're right. So there are different drivers. Like one of them is industrial clusters. That's the way we think, hydrogen projects should work. That that's already the case. For example, in Humber and other regions, there are so many industries that may actually use hydrogen as feedstock or to replace natural gas. They already have some demand for hydrogen that's already happening in industrial clusters. But I guess another example, maybe that's why that question was asked, is some of the industrial users may become hydrogen producers, and industrial companies may become hydrogen producers and actually sell hydrogen to other companies nearby. For example, there's potential to convert, I don't know, blast furnace gas and some of the gases produced, internal gases and fuels produced by industrial users such as iron and steel, that can be converted into hydrogen and sold to nearby users. So that's another example which that some of the industrial companies and organizations may become an active contributors to the hydrogen economy. So that's another example, and we're already seeing some potential for that in certain clusters. And beyond that, yeah, I mean, as I said, this will involve not just industrial organizations. For example, my company is involved in a project called GigaStack in Humber in the UK that involves Ørsted as a green, hydrogen renewable energy producer, offshore wind producer, ITM Power as the electrolyzer provider, and also the kind of refinery in the region and potential other users who will then use the hydrogen. I guess for hydrogen projects, we will need the full supply chain to be in place, because currently we don't have much on both supply and demand. So you need to create both supply and demand within the same initial projects. That will hopefully create the whole hydrogen economy. But yeah, definitely the industrial symbiosis or clusters will play an important role in that transition.
Okay, thank you very much for your answer. I would like to add a question. So my understanding is that you are very vividly supporting hydrogen as a means to decarbonize industry. Could you imagine to put another hat on your head and argument against hydrogen as a means to decarbonize?
I guess so. We're working with the Committee on Climate Change again nowadays, and hopefully we'll publish a report soon. I haven't mentioned anything in this report because that's still ongoing. And so the reason why hydrogen may, or at least we thought would play an important, really big role in industry in the UK is because electricity is really expensive for industrial users. But if there's a way to lower the electricity cost and renewable electricity cost, then that makes electrification more cost effective than hydrogen, especially for indirect heating applications and lower heat applications, etc. Hydrogen could still play a role, for example, for, as I said, high heating applications. But again, this is not as I said, that's why I tried to show that kind of initial first slide showing a wide range of technologies and portfolio of technologies, because I'm also worried when I see stakeholders going out and just saying we only need hydrogen, that's it. Nothing is as simple as that. And likewise, electrification only, unfortunately, may not solve all of our problems, and we may need hydrogen in certain areas and certain countries, or CCS in other, pretty much most process emissions. But still, some countries may prefer other ways to decarbonize those sites. So I think in terms of the key challenges of hydrogen, I guess the way you produce hydrogen is always kind of difficult one, because it's not available at scale. And, as I said, even one industrial user may require a significant amount of hydrogen straight away. If you have a couple of sites, you're talking about terawatt-hour scale, hydrogen demand straight away to decarbonize those industrial users. So that's not available today. The only way to make it produce it at that scale could be blue hydrogen, and we know blue hydrogen is not very popular everywhere, and especially the CCS, for example, in Germany, there is not much appetite from the German government on CCS and even blue hydrogen. And in certain countries, think green hydrogen is the only way to produce hydrogen. And then for green hydrogen, we need to wait until that's scaled up and that level of hydrogen can be produced. Again, the questions around what's the electricity source for green hydrogen? If you use grid electricity, it doesn't make sense. If you use dedicated renewable energy, that may be more expensive. If you use just as a kind of, to avoid wind curtailment, for example, when there is no demand, you can produce hydrogen as a storage, but then the amount of hydrogen production is very low, and that doesn't address the industrial demand. So anyway, there are some couple of issues regarding the production of hydrogen and then storage of hydrogen. But I guess in terms of the use of hydrogen, when we talk to the industry, especially if they're using natural gas, they think switch from natural gas to hydrogen could be straightforward. So I don't think that's very controversial. I guess the way we produce and store hydrogen may be a bit more difficult and it's a tricky one. over the next decade or so.
Okay, so thank you very much for your insights, and I'm happy to see that you have so many projects ongoing in the UK and on the industry. I was very happy that you have joined this conference with your insights from the UK. So thank you very much for your presentation, Emrah. There are no more questions in the chat, nor here at Zoom, nor in Hoover. So, but the chat and Hoover will be open. So please check if there are any questions for you. I was very happy to chair this panel on deep decarbonization in industry, and I would really warmly want to thank you, all of you, both the presenters as well as to the audience for your presentations, and also for the questions and for your attendance. So I think it was a great conference. We learned a lot. We have seen a lot what other researchers are doing. And we see how many questions are still open and that we need to find some more solutions on doing next steps for deep decarbonization of the industry. So I think until we lately see again in the next 2 years at the next eceee industry, there is a lot to do for us. And I'm glad to see you all again, latest again in 2 years at the next eceee industry. So a very warm thanks to all of you. I hope you enjoyed the conference, and please join the after session at 4 this afternoon. So yeah, and with that, I will close the session. Thank you very much and have a nice time.
Thanks, bye.
Bye.
Bye-bye.